Hello, I am Min-Fu Li. I am a professor in Department of Electrical Engineering, Changchun University, Taiwan. The title of my presentation is Stability Analysis of Wireless Powered Communication Networks. This is the outline of my presentation. In the first part, I will give you a brief overview of wireless powered communication networks. It is well known that there are numerous battery-powered wireless devices in IoT. Hence, replacing batteries for wireless devices may become highly costly. For example, in biomedical sensors implanted inside human bodies or in the mesh system with a large number of wireless sensors. Energy harvesting and wireless energy transfer technologies are possible solutions to overcome such issues. Since wireless energy transfer technology can provide more efficient and stable power transfer compared with energy harvesting, and thus it attracts more attention recently. Wireless energy transfer technology mainly fall into two categories: near field and far field. Near field wireless energy transfer technology may use inductive magnetic resonance or capacitive coupling technique. It can support high power transfer but only over a short distance. Far field wireless energy transfer technology is based on the radio frequency radiation. It can support long-distance power transfer but only with a low power. The focus of this paper is on the far-field wireless power transfer technology. The challenging issues in far-field wireless energy transfer include unstable charging rate, doubly near-far problem, energy transfer efficiency, and interference with information signals and health concern. The communication network with wireless powered devices is called Wireless Powered Communication Network, WPCN. In WPCN, the main concerns are data transmission performance and energy shortage issue. WPCN can use dedicated energy transmitter or hybrid access point to transfer power. In the dedicated approach, data access point and the energy transmitter are separate devices. Such an architecture is simple but may be costly. In the hybrid approach, hybrid access point can transmit energy and information. So it is cost-effective, but there exist several challenging issues, such as the interference between energy packet and the information signals. Hybrid access point can be half duplex or full duplex. In half duplex energy and the information cannot be transmitted simultaneously, so the harvest then transmit protocol is proposed. In harvest then transmit protocol, time division multiple access approach is used. That is, one period for energy transfer and the other one for data communication. In full duplex HAP, energy and information can be transmitted simultaneously. However, the self-interference exists between energy transfer and the information transmission. If cell interference can be cancelled effectively, then full duplex HAP outperforms the half duplex HAP. There exist several challenging issues in WPCN. For example, energy transmitter should be dedicated or hybrid, and the energy receiver should use time switching or power splitting. Also, what battery capacity should be allocated at the receiver, and how to design an on-demand energy transfer protocol to improve the energy transfer efficiency, and how to design an energy-aware medium access control MAC protocol for data transmission. Polling or carrier sense multiple access based MAC protocol would be better. In addition, what is the stability condition of a WPCN? That is, given the network bandwidth and the energy charging rate, how many wireless nodes can be deployed? The focus of this paper is on the stability analysis of a wireless powered device. The term stable in this paper indicates that the average queue length of data buffer exists and is finite. For a conventional McCollum MM1 queue, the stability condition is trivial. That is, the packet arrival rate lambda must be less than the packet service rate mu. However, for a wireless powered device with a finite energy buffer, given the wireless charging rate E, data packet arrival rate lambda, and a finite battery capacity C, under the McCollum model, what is the stability condition of a wireless power device? In this paper, we derive the stability condition of a wireless power device. Our system model is described below. In our proposed system model, a single wireless power device is considered. The energy is discretized into energy packets. The wireless powered device contains a finite energy storage buffer of capacity C and an infinite data buffer. Packet arrivals of energy and data at the wireless device are independent person processes with rate E and lambda respectively. The transmission time of a data packet is exponentially distributed with parameter mu, and each data packet transmission consumes exactly one energy packet. The system state can be denoted by a two-dimensional vector ij. I is the number of data packets and j is the number of energy packets. Hence, the system state transition diagram can be plotted as this figure. Next, we will derive the stability condition of a wireless power device. First, based on the system state transition diagram, the global balance equations can be obtained. Let the stationary state probability of state ij be denoted as Pij. According to the flow conservation law, at each state, the total arrival rate must equal the total departure rate. Thus, for the state ij, where I is not less than 1 and j is between 1 and c minus 1, for example, state 22, arrival rate consists of 3 parts. Departure rate also consists of 3 parts, so we have the first equation. Next, consider the boundary states. Let j equal 0, for example, state 20. According to the flow conservation law, we can obtain the second equation. Similarly, for the boundary states, let j equal c, for example, state 2c, we can obtain the third equation. For the boundary state, let I equal 0, for example, state 02, we can obtain the fourth equation. Finally, for states 0, 0, and 0c, one can obtain the last 2 equations. In the transition diagram, one can also partition state states into two disjoint sets. For example, the set inside and outside the blue circle. According to the flow conservation rule, the total arrival rate into a set must equal the total departure rate out of the set. Thus, we can obtain the first equation. Similarly, if the states are partitioned into the sets inside and outside the green circle, one can obtain the second equation. Since the sum of the stationary state probabilities of all states must equal 1, then taking the summation over on I or j on these two equations, the next three equations can be derived. Next, we use the probability generating function to derive the stability condition. GJZ is defined as the summation. Now set Z to 1, and based on this equation, we can derive the recursive equation. And set J to C and Z to 1, and based on this equation, then one can derive the equation. Then, based on these two equations, use the recursive equation iterated backward on J starting from C. Then we can derive this equation. Then taking summations on J, since this term is equal to the summation of stationary state probability of all states, it must equal to 1. Also, this term must be greater than 0. So we conclude that this term must be greater than 1. So this is the necessary condition for system stability. This equation inequality can reduce to this inequality. One can also show that this condition is also sufficient for system stability. The detailed derivation can be found in appendix. Next, I will show you some numerical result. The stability boundary of the wireless powered device is plotted based on our analysis result. The unlimited energy case, which reduced to a simple MN1Q, is also included for comparison. According to this 3D plot, at a small e, the stability boundary of the case with a finite charging rate is significant, deviate from that of the unlimited energy case. Even at large E and mu, the stability region of the case with a finite charging rate E also significantly shrink compared with the unlimited energy case under a small energy storage capacity C, for example, C equals 5. That is, the stability region is strongly affected by the wireless charging rate E and the energy storage capacity C. To demonstrate that the derived stability condition is necessary and sufficient, simulations are conducted to investigate the average Q length of the data buffer. The analytic stability boundary, that is, the vertically dashed line, is also plotted for verification. Obviously, the stability regions are strongly affected by the energy storage capacity C. In addition to the data packet surface rate mu and the wireless charging rate E, according to the simulation result, the average number of data packets grows abruptly only when lambda is close to the stability region. Additionally, the queue length of data packet is always stable whenever the packet arrival lambda is below the stability boundary, while it becomes unstable when lambda is set over the vertically stability boundaries. All the simulation results show that our derived stability condition is necessary and sufficient. Finally, our conclusions and future work. First, the stability region of the wireless powered communication network significantly shrinks compared with the unlimited energy case. Second, the stability region strongly depends on the wireless charging rate and the data packet arrival rate and the energy storage capacity C. In the near future, we will consider a more general model with multiple wireless powered devices. Also, consider the effect of medium access control MAC protocols such as polling or carrier sense multiple access on the stability region. Also, derive the average data queue length, data packet delay, and the energy shortage probability, etc. Thank you for attention.